Hey. Oh, I'll tell you what, let me do one more thing here and dim the front light. There. That good for everybody? Yeah. Yep. Okay. We're still learning how to play with the element, play with the toys here. Okay, let's see. Make sure I'm not mute. Yes. Okay. Hey, Dan, you can still hear me, right? Okay, cool. Okay, folks, welcome to the October Northwest C++ Users Group meeting. I'd like to thank our sponsors, City of Bellevue, for sponsoring our meeting room. And please, we're still using the Microsoft Code of Conduct. I'll make up a new one at some point, but for the moment, we'll just pretend we're at Microsoft and use their Code of Conduct because just be nice to everybody and we're good to go. It looks like Bellevue City Hall is going to be our new meeting space. This seems to be working out pretty well for everyone. Just a note, the Rust user group sounds like they're also moving here permanently. That meeting is going to be next week for the folks in the group who like to attend both. I think maybe we finally just got that sorted out. We're booked here through the end of the year, and as long as we don't burn the place down, I'm sure they'll invite us back for next year. So already mentioned the Code of Conduct. We are also looking into getting our after meeting gathering started again. Looks like we're starting to get, more attendance here, so people are getting used to it. And I don't know, Peter and such will talk about that at some point and get that going again as well. Somebody was also mentioning, hey, it'd be great to get pizza going again. We'll kind of see what we can do with that maybe in the new year. Oh, one more announcement that's not on the slide. I am starting to look for speakers for 2026. If you would like to speak or you know somebody who would like to speak, I currently have February on open. So just ping me or have your friend ping me or whatever, and we'll get you signed up. If you don't sign up, I'll come up with something and then you can listen to me drone on about something for another hour. How's that for motivation? Okay, so our feature presentation tonight is Greg from Undo.
Correct.
Talking about agentic debugging. So we'll turn that over to him in just a moment. Please keep your questions short and focused so everyone gets time to interact with the speaker. Please don't interrupt the speaker or other members when speaking. Also, just a quick note, if you're on that side of the room, you're off camera. If you're on this side of the room, you're on camera. So we actually do have a few more people in the room that are all hiding off camera.
Very shy.
Yes. Okay, with that, I will stop sharing. And Greg, if you want to go ahead and share yours, and you should be good to go. Okay, and let's see. Go ahead and unmute your mic, Greg. There you go. I'll turn mine off.
The sharing is not playing games, not playing ball.
Ooh.
Let's stop sharing and start sharing again, see if that goes better. But you see, we tried it this morning.
Of course we did. We tried it and everything was
and it worked
working.
fine, right? Okay, time screen, share. Unbelievable. But we literally tried it this morning and it worked.
Okay, and it's interesting that it's not showing up there. I've got it.
Oh, hang on. No, yeah, you got it.
I've got it, but it's not showing on the monitor.
Oh, is that right? You're seeing
bizarre.
That is bizarre. What?
Okay.
Maybe it's a screen
progress.
resolution thing. Maybe.
could be.
Let me try it. Let me try that.
If it,
That is very weird because yeah.
that is totally weird because I've got it, so I know you're broadcasting.
Did you say that's 1080p?
I believe it's 1080p, and
Okay.
if that doesn't work, we can stick you
We'll
on.
just do that. Yeah.
We'll switch positions and stick you on
That's
HDMI.
so. What's 1080 and is that 12? No, is that? Yeah, 1280 by.
Yeah, 12, that'll do it for sure.
Are you sharing a screen or are you sharing through PPT?
Sorry.
Are you sharing your screen or are you sharing through PPT?
I know sharing the screen. Yeah,
Yeah, he's
it's just
sharing the
it's
screen.
this whole screen share.
If you try PPT live, then
Oh no, but I'm not using. I'm doing demos and things, so it's
Yeah.
not just PowerPoint.
Okay.
But the thing is, I'm getting it on mine. So.
But you're not now because I've changed
I'm
it.
not now.
So let me retry.
Yep.
This is going to work. I'm very confident. I'm not confident.
So why does this say projection of your
Perfect.
All right, there we go. So I think
that
that was
a
just
projection of his screen.
too
so we're
many
good.
pixels. I
Too
think
many
is the
pixels.
problem. There we go.
Okay. And now for our featured presentation.
All right. Hey, everyone. So yeah, I'm Greg. I'm from undo.io, and we're going to talk about all awesome things with debugging, with agentic debugging through time travel. I'll show you what I mean rather than try and explain it. I think that'll go better. Oh, come on.
Mine's frozen too.
Okay. So that. All right.
There it goes.
Let's see how we go.
That's just weird.
Okay. All right. You might know this quote. This is from Brian Kernighan. He's kind of one of the fathers of modern computing, inventor of C and Unix, among other things. It's quite a well-known quote, but just in case you haven't heard it, it says, everyone knows that debugging is twice as hard as writing the program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? I think really what Kernighan means here is like, keep it simple, right? Give yourself margin for error. You're probably not quite as smart as you think you are. And I think that's true, but I think there's an interesting like corollary to this, which is I just think totally underappreciated in the industry, which is that this means that debuggability is like the limiting factor on how good our software can be, right? Whatever your metric for good is, how fast it runs, how small it is, how quickly you can write it, or whatever your metric for good is, then if you make it twice as debuggable, you'll make it twice as good. And it never ceases to amaze me really how little attention this seems to get. And when I talk about debugging in the context of all the kind of AI excitement that's happening right now, and it's like even more relevant than ever. So all the AI stuff right now is focusing on like the 10% of the problem. If you look at what a developer does during the day, generally they're going to spend about 10% of their time actually typing in the code. Way more time is spent. It's not time spent in meetings and all that stuff, but way more time is spent understanding and debugging the code and just the process of typing it in. All the excitement right now with AI is all about the generation of code. It's attacking that 10% problem that's now going to perhaps go to 2 or 3% of the time spent typing code in, but we're not addressing that debugging thing at all. And I've never really understood it, and I'm here to change everyone's mind one person at a time. Oh, come on.
There it goes.
It's bugs, right? This is a little warm-up question to get us in the habit. I want to get you all off the fence, okay? So you have to give, I'm going to ask 2 questions, one after this one and one after, and you have to give precisely one answer. You can't say it depends or both or neither, precisely one answer. So I want a show of hands between dogs and cats. So dogs, show of hands for dogs, you have to give precisely one answer, okay? And cats, ooh, okay, pretty close, pretty close. The right answer is dogs. But this is good. So we're off the fence. So now I'm going to ask one much more difficult. Let's see if the slides flip. No, that won't happen. Okay, it's going to get tedious. Right. We're going to do the same exercise now, but for printf debugging or the debugger. Okay, there's no it depends. You've got to choose one. So printf, you're going to debug with printf. Show of hands. And precisely one answer. Okay, so that means everyone else is the debugger. Show of hands for debugger. Wow. Okay, that's like it's normally pretty down the middle. That's a very I'm preaching to the converted. This is I don't know if this is a good thing or a bad thing, but
There's a big
excellent.
asterisk with mine, even though you said I had to choose.
Yeah.
And that is, most of the time I can't use a debugger because of what I'm doing. And
Right.
I need print up anyway.
But so if one is available though, then you would, yeah. So yeah, the thing is, it's kind of a like, deliberately kind of provocative, nasty question. This flares up online like twice a year, every year, as reliably as the clock's going forward and backwards. It seems like people like fighting between, and of course it depends on the context, depends on a lot of stuff, and basically both kind of suck, right? So for printf, obviously I can't, if I'm doing print style debugging, I can't ask any new question of my program without recompiling and rerunning the program. So you probably remember this XKCD cartoon from a few years ago that they're compiling. What are they compiling? They're compiling a printf, right? 85% of builds outside of CI that compile is because somebody's added a print statement. I completely made that stat up, but I stand by it, right? Prove me wrong. So on the other hand, the debugger doesn't tell you what happened, it tells you what's happening, right? I mean, okay, you can get backtrace and it gives you some kind of clue, but generally you can ask any question of your program in the state it's in right now when you're stopped at a breakpoint or whatever, but you can't ask what the prior states were. And debugging is really kind of process of, slides can not work, process of reasoning backwards, right? We're looking at like what happened. So there's a free license of undo, which is, the animation's even not working, which it says here is worth $7,900. So if you want to take a thing of the capture of that QR code, you can enter the raffle. And as we don't have a huge number of people here, your odds of winning are pretty good. Like sometimes this, like literally, last time I did this was last week in the Netherlands, and there was like 100 and something people in the audience. So your odds are good. Yeah, worth. It says here worth 7,900. I like to say it's actually worth a lot more than 7,900. It costs 7,900. These are some of our customers. People are using it right now. Part of this is just like, it's a bit of a flex, as I like to say. Pretty proud of the customers that we have. But the point really of showing this slide, apart from that flex, is what I'm going to show you today is real. Like, it's not just works on toy programs. This works on real world, complex, millions of lines of code, at scale stuff. Good news is I don't have that many slides. So yeah, so the thought process is, how did that happen, right? That's what we're thinking when we're debugging, right? So it's a past tense question. I don't mean how did that happen. I'm not going to go. I don't mean how did that happen. What I mean is we've got expectations of reality, and at some point, the animations aren't even going to work. Oh, okay. So at some point, reality diverges from my expectations, and the process of debugging is figuring out where is that divergence of reality from my expectations, right? And let's get.
You could just leave it on that.
I think, yeah, probably some of them have got animations. Anyway, it doesn't. We'll just have to, yeah, we'll just have to get on best we can. So yeah, it's kind of like doing the jigsaw puzzle, right? Or maybe you're Sherlock Holmes. You're getting clues. You're gathering clues as you go, and maybe it feels more like that than Sherlock Holmes some of the time. I think if you just step back a little bit, what makes bugs hard to find? There's two axes that make bugs hard to find, right? One is how long elapses between the bug itself, between that bad line of code executing and you noticing. Obviously, the longer it is, the harder it is. This is why assertions are a really good thing, right? Because what assertions do is narrow that time. And it's why bad results is always the worst kind of bug. Like and it's just, the program runs and the results that come out at the end are not what you wanted. They're awful because it's a long time. The other axis is how deterministic is the failure. Does it do the same thing every time? If it does, I can just add my print statements or step through in the debugger, and like, it might be tedious, it might take a long time, but eventually I'll get there. If it behaves differently every time I run it, it's like doing a jigsaw puzzle, but every piece of that we pick up is for a different picture, right? And we're trying to figure out what time that's when we get these highs and bugs. So what I want to get into is I'm going to show you time travel debugging. Now, I choose this image to represent time travel. This is the H.G. Wells Time Machine film, and obviously novel before that. I like this partly because I think that picture is kind of cool, but also because unlike the more modern time travel stories where everyone's always going back and changing history, that's not what this is. This is not about going back in time and changing things because, like paradoxes and everything. But what it does is just like in H.G. Wells, you go back in time and you observe, and you can see what happened, and you can see how we got here. And I think this is really useful because we get the best of both worlds. The print style debugging gives me that history of what happened. It gives me a story of my program's execution. Debugger lets me ask any question of the program that I want without rerunning it. And with time travel, we get both. So that's enough of the slides. Let's show what this actually looks like. And what better way? Okay, let me just resize that. Best way is we're going to play Doom. But I'm not just going to run Doom. I'm going to run Doom with this live record thing prefixing running Doom here. So, let's get sound because it's better sound. So you'll observe that I'm not really a very good gamer. That's what we're trying to do here. Okay, that'll do. Right. Now, what I'm going to do, this is a code base that's like completely unfamiliar to me, right? I only know one thing about this code base, but using time travel, I'm going to navigate through in the debugger to find the exact moment in time, the exact line of code where I killed that zombie. So I'll just remember how to do this. I'm going to get this display up. This is going to show me, if I do this right, it's going to show me, I haven't got a lot of pixels here. Hang on, this is going to be tough, but it's okay. I think we can do it. So that is the undo file. See one more I was playing around earlier, but this is the undo file of that recording that I just made. So it contains everything that program did, every line of code that ran, every piece of data. And you can see it's actually pretty modestly sized given what I just described. Let's load this into VS Code. You just have to forgive the lack of screen real estate here, but I think we can make this work. So there it is. Okay. These. So, all right. So this is, I didn't want to close that window. Why did I do that? I think that one. Okay. So yeah, I said there's one thing about this that I know, and the one thing I know is there's a pix map called iVideoBuffer, which is a 320 by 200 pix map for the screen, right? That's the only thing I know about this program. I'm going to use that to traverse through this small but non-trivial piece of code. So by updating that, what this should do, so this is at the end of time now. I'm going to pin this to the top, always on top. So this is the end of my recording. So kind of like a core file at this point. I've got everything. I've got every piece of memory, every register value, and I'm at the end of time. So yeah, I want to go back to when I killed that zombie. Well, I'm going to pick a pixel here, a bit of blood there. So by clicking on that, I can see that is this value there. So if I look at iVideoBuffer 182 plus 144 times 320, that should be like a little bit of red, a bit of blood. Now, if I want to go back to, I'm going to quickly switch away, and I'm going to do something. I want to run two things in parallel, so that we can compare them. So I'm going to run this one in the command line version. Oops, like that. Okay, and I'm just going to extend with something called explain. So this is now what Explain is going to do is connect Claude to that recording and kind of allow Claude to see what the hell is going on through the recording. So Explain, find the time in the program execution where the second zombie was killed. We'll let that chug away, and I'll go back to do it. So I'm going to do it automatically with the AI, and I'm going to do it by hand. And we're going to rate the two things are going to race, and we'll see if I can beat the AI. So yeah, right. How am I going to do that? So why don't we go back? The nice thing about with a good time travel debugger is you can follow not just the code back, but you can also follow the data, and it's really always about the data. So I can say, when did that pixel last change value? And that should take me to something that's kind of relevant, right? So if I go last $1, okay, so it's taken me back in time. So I'm now 99% of the way through rather than the end. And I'm in this draw column, yeah, it looks all about right. Okay, I've got draw sprite. So this kind of looks good. I'm going to, let me just move that down a bit. Let's do this button here. This is uncall. This is going back to the call site. It's a little bit like popping up the call stack, but the program is really unwinding all the global state and everything is moving back. And what I want to do is just get back, so I can see this sprite thing in my call stack here. I'll go back one more, and now I've got this sprite. Let's get rid of that. And this sprite called Spr. And I can see it's got a bunch of things. It's got some kind of, I don't know what these coordinate sort of things are. Let's follow that back. Let's go back to when that sprite last moved and see if that. So another last operation. So we're going back in time. This time we're now to 93% of the way through the program execution. And I'm in this project sprite call. And what have we got here? So there's my sprite. Okay, I've got thing. That's probably some sort of arbitrary object type thing. And that's got a whole bunch of properties. We've got state, health. So I've followed that back. That's the sprite that maps onto my zombie, and it's got a health of 0. So that's probably a pretty good place to go look and see like when that changed. So if I go last thing, health. So it's going to search back through time. Okay, so now we're 86% of the way through, and look, the screen is updated. In fact, so this is the point. So health was 0, now 10. So I've gone back in time from health to 0 to 10. So it's now alive. It was just about to die. Okay, this is like, it updates the state, but it hasn't like updated the screen yet. But if I remember, so I'm going to put a bookmark there. I'll call the bookmark killed, so I can go back here a bit later. And I'm going to hit this. Remember previously we were looking at when it was updating the screen. I want to get back to that screen update code. So let's undo, which is a little bit like pressing the back button in the browser. It goes back to where I previously was observing. So here we're back to 93%. If I go back here, right, 99%. Oh yeah, this was it, de-display. So this is my sort of, there's something updating the display here. Cool, so let's go back to that bookmark. You go bookmark killed. So now I'm going to put a breakpoint on de-display, and I'm going to continue forward. And now this is at the beginning of updating this display. So if I finish to return from that function when the display is updated, there we go. Look at that. That is the precise moment where that zombie got. Do you kill zombies? I think they're already dead, but whatever it is, that's like. Now, obviously I have done this before a few times, but genuinely you can see how you can navigate through complex code bases by just following this ability to catch onto the data and follow that kind of thread. Right, repeated uses of last is super powerful. Let's see how the AI did. Now, obviously, running. That wasn't supposed to happen. Okay, well, good news is I beat the AI. Yeah, running AI demos is generally bad because anything can happen. That was particularly bad, but at least you know I'm not faking it. Just like that. So let's try that again. I'm going to show something else now as well. Actually, I'm going to leave that. I'm going to leave that running. And so, oh yeah, no, sorry, so I'm going to do something that I think is even more impressive, and this is something that we're working on. This explain thing is available now. Let's get rid of that. This is a real bug in Python. If I run that bit of Python, I know this isn't a Python meetup, but who wants to guess what that bit of Python's going to do? It's a trick question. It's not really, but let's run it, right? That's not supposed to happen. That Python segfaults. Python is a memory-safe language, right? So this obviously, by the way, this is the Python. That's the Python interpreter that just is on my Ubuntu machine. So this obviously is this must be a Python bug, right? It should be. I mean, it's its own. It's just a few lines of Python. It shouldn't end in a segfault, and it is a Python bug. And this was very recently discovered, and it took the Python maintainers a couple of weeks to get to diagnose what was going on. Now, to be fair, they've got day jobs and things. It probably wasn't 2 weeks like full time, but it's a pretty serious Python bug that shouldn't be possible. And it was non-trivial for people who really understood Python code to get to the bottom of. So we thought we'd see with we're working on, we've got 2 MCP servers. So the one I'm showing you, right, whatever, that's not going to work. But this one is actually, I think, more impressive anyway. So if I run, anyone use Claude Code? So let's just make sure that this is working. Yeah, so we've got an MCP server here connected to our Claude Code, which teaches Claude how to kind of use tools. And what Claude is able to do now is reach into our recordings, and based on something that we call post-failure logging, which is, you know, I was really kind of down on printf debugging, but actually it's got a place in the world. And the nice thing about print style debugging is it gives you a kind of story of what the code has done. So wouldn't it be nice if you could take one of our recordings and do kind of post hoc printf, like post-mortem printf, and say, what would it have looked like if only I had a printf on line 42? And that's when you can do that. You've been able to do that for a long time in the product. And we've now connected that up to Claude so that Claude can start asking these, because Claude, like the LLMs, like logging. They like printf style debugging because they like lots of logs, and because that's like how they work. And there's a little bit more to it than that, but that's essentially the thing. So if I actually, let me just, so I've got, so this is my prompt. This is just persuading Claude that it really is very good at what it's doing, flashing it into working better. And then this is really the thing, which is basically just saying, like, yeah, there's a bug, it's segvid, what the heck's going on? So please diagnose the bug as per the instructions in. Now, this takes a little while, so I'm just going to set that off going because it's pretty subtle, but we'll just let that run. So yeah, right. Who's anyone used time travel debugging? Like, because Microsoft have got a version of it, and you used it a little bit.
A little bit.
With the Microsoft one, or
no,
which one? RR.
Yes.
Yeah. Yeah. Okay.
It was a long time ago.
Yeah. And there was someone over here. I saw a hand go up. Yeah, you've used it. Cool.
Yeah, Microsoft.
Yeah. Yeah. You like it?
Yeah. I use it a lot.
Yeah. I mean, it's magical. So who's heard of it at least? Right, yeah. So this is what I usually see. Right. Most people have heard of it. A minority, actually, percentage-wise, we're doing really well in this room. What I usually see, like I said last time, I had like 100 and something people in the audience, and almost all the hands went up to having heard of it, and about 3 hands went up for having used it. And I'm like, what's going on? And it's just, yeah. Once you start using it, you'll never go back, really. But well, that's my claim. you should try. That's the one thing I'm convinced of is that everybody should try it. I know it can't always, it's not always available, etc. But if you're in a platform where you can use it, like you totally should. Let's just see how this is. So this is going along. So we can see, right, okay, so it's got these timestamps, which is this is the nice thing about this approach with connecting LLMs to recordings, by the way, is that it's kind of an antidote to hallucination. Okay, so what's actually happening here is the LLM is coming up with hypotheses about what might be going on, and then it can kind of look inside the recording and see, was that real? It also tells you what it's been doing, and then you can go back and check. So yeah, I mean, LLMs are wonderful at writing code. I mean, it's just extraordinary. I mean, they're not perfect, but it's just, who would have thought even a few years ago they'd become as good as they've become. But they're really nowhere at debugging it and understanding it. Like, and if you give an LLM some symptoms of a bug, it will generally give you the most likely plausible explanation based solely on the symptoms, like without actually looking at the code and understanding what's going on. This looks like it's doing a good job, so it's always a bit always a bit risky doing an LLM thing live, but it's got an object that was already freed, so it can really test this, right? Because I think there's a use after free. That's kind of the hypothesis. It can then look through the recording and it can find when was the object live, when did it get freed, it's been used, and you can see it's definitely got use after free. And so I think this has the potential to make the LLMs good, not at the 10% chunk of the problem, but at the much larger 50% chunk of the problem. I've got a whole bunch of slides on like how this works, and we'll get into that because I think it's pretty interesting. But questions before I do that?
What's getting recorded as the system runs? And actually repeat the question too, because your mic won't pick him up.
Yeah, so the question is what's being recorded as the system runs? And the answer is just the non-deterministic inputs. So let me show you how that looks. So we've got a bunch of snapshots here, which are copy on write snapshots of the program state. And we have events. And these are all the events. These are non-deterministic operations, right? So basically, these are all system calls. But whoops, didn't do all of that. Let's do that again. I keep going all system calls, but I'll see if I go through here. I've got some thread things, new threads being created, thread switches. Here I've got some shared memory fix-ups. So these are all the different kinds of non-deterministic events. So when in the demo I like go back one line, what's happening underneath is that's going back to a snapshot and it's playing forward to just before where I was. So it's always actually going forwards. It never really goes backwards.
So what is it? What is in a snapshot?
What is in it? The snapshot actually is our snapshots are based on fork. So when you fork a process, it's really convenient for this, right? Because what you get is a copy on write copy of the entire address space and the registers. And that's it. That's what's in the snapshot. But it's copy on write, so it's nice and efficient. And then that just allows us to go back to one of those previous snapshots and just like play that forward. But of course, the trick is when we play it forward, we have to make sure that it follows exactly the same path that it did in the record mode. And that's why we need all these non-deterministic events to be stored. But these are a very small proportion, like 0.01% or something of everything that the computer does. So we get into that, right? So yeah, so kind of we were saying that the debugging is like, how did that happen, right? And the kind of computer science way of asking that question is, what was the previous state? And I make that bigger? No, it doesn't seem to want to do that. Whatever. Anyway, yeah, what was the previous state? So there's kind of two ways. When I go back to the prior states, I can try to just save it as I'm running, because when the computer's running it, it executes like one of these statements. The previous state is gone, doesn't exist in the universe anymore, right? So we've got to somehow save it. Or we can either save it or we can recompute it. And if I've got one like this first statement here, this a equals a plus 1, that's a trivially reversible statement. If I've just executed that statement and I know the value of a, then I know the previous state of the program, right? It's obviously a minus 1. But the second statement there is not reversible. I have no idea what was the value of a before that statement ran. In fact, even the first one isn't really reversible because I things like flags in the flags register will be updated. And also, I don't even know what the previous statement was. Maybe there was a goto that got me there, right? So recomputing it, for sort of going backwards, doesn't work. There's actually a very interesting field with reversible logic, trying to make computers that are genuinely reversible, because it turns out that there's a kind of E equals MC squared kind of equivalent for information. And so to destroy information consumes energy. And some super smart people worked out if they made a computer that didn't destroy information, it will actually consume less energy. And it does kind of work, but it's like super, researchy. Only in a few universities, there's no commercial hardware is reversible. But they are deterministic, right? You can think of a CPU as basically really fancy, big function. F of x gives me the next iteration of x. That's really what a CPU, where x is the entire memory state and register state. That's what the CPU does, right? They are inherently deterministic, repeatable things, except when they're not, but mostly they are. So that's, yeah. So by having these, as I described before, snapshots and event log, we can be much, much more efficient, right? Because the other alternative is to try to store just the diff each time. But if you think about it, like every instruction that runs, something's changing, otherwise you're live locked, right? At least the program counter is changing and probably some other program state's changing. So I'm probably saving 8 bytes every single instruction that runs. Billions of instructions every second. That's just an enormous amount, even if I'm just storing the delta. So I don't want to do that. You want to recompute as much as possible, and that's how this works.
Sure that the re-execution is a deterministic reproduction of what came before. You can get certain situations with threads or things where things are loaded in different ways, and they finish in a slightly different order, and therefore your data structures are different.
Yeah, yeah.
Now you don't tickle the bug.
Right.
That you did.
Right. So we have basically this is different in Windows, but in Linux and Unix type operating systems, there are 5. Another way of saying non-deterministic is predictable. If I've got, like, I know my program memory state and register state is the operation predictable, and I've got 5 sources of 5 things that are unpredictable. The most obvious is system calls. If I get time of day, every time I do that, I get a different value. In fact, if the system call result is predictable based on the program state, then it shouldn't be a system call, it should be a library. You correctly asked a thing about threads. So there are a couple of different ways to deal with this. I'll get into different implementations of it as we go down. The simplest way to deal with it is just basically to cheat and to serialize the thread's execution, and still allow preemptive multi-threading to happen, so you can still reproduce almost all race conditions. But we only let one thread run at a time, and then record when thread switches occur. So it's a bit like in the old days running on a single CPU kind of system. You've got asynchronous signals in particular. So we've got to capture those. We do that through ptrace. Shared memory accesses are kind of fun. So most memory holds the property that what I read was the most recent thing that I wrote. It's kind of how memory works. But if the memory is shared with another process or with a device or with the operating system or something, then that's not necessarily the case. So what we have to do is, when we read from shared memory, see, is that the last value that I saw, or has it changed under my feet? And if it's changed under my feet, that goes in as an event. And we saw those mem fix-up events. And there are some machine instructions actually that are non-deterministic. So read the timestamp counter on x86 is an example of that. Give you a different thing every time. Many modern CPUs have a get me a random number instruction. So we have to trap those and store those away. But that's it. Capture those 5 sources of non-determinism. That's all you will, then you are guaranteed to replay exactly faithfully the original execution.
Question.
Yeah.
So when you take snapshots, how do you decide on the samples? Is it you take a snapshot after every instruction that got executed, or is it a
no, far less frequently than that. In fact, what happens is when it's running under record, we actually take snapshots very infrequently. We'll usually maintain actually 3 or 4 snapshots in the entire program execution. So if the program's been running for 10 minutes, probably taking a snapshot every few minutes, because we want to kind of get out of the way as much as possible. But you can also create snapshots in replay mode. The important thing to understand here is that the snapshots are just an optimization. If I were patient, I'm not very patient, but if I were a patient person, then I don't need any snapshots. I've got the starting state, I've got my non-deterministic events. And so every time I move around when I'm replaying the debugger, I could go back to the beginning and play it forward where I want to be. And if the program was running for a few hours when I recorded it, that would be very tedious. So we have these snapshots around just as kind of an optimization at replay time. And then what we try to do is we can infer, like, the point where you are now is probably interesting because you're stopped there at a break point or a signal or something. And so that's an interesting point in time. So we'll keep snapshots kind of close to that so that when you're moving around, you know, when I'll show you in here, you can see this, like, if I go back, you know, it's like, it's, you know, basically instant, right? Even though that was a pretty, I didn't run that demo very long, but probably a minute or two, right? But I can ask it. No, I can't. Okay. Sorry, there is a way to ask it. I can't do it. But yeah, anyway, it was running for a minute or so. But yeah, that's it. And what you'll see is so, but you can create snapshots at replay time as you're going through history. But you can observe this if you go back enough. If you step back enough times, it's quick until eventually you step off the edge of this most recent snapshot, and then it has to go back to an earlier snapshot and play that forward, and that might take a little while, especially if it's been a long-running recording. But that doesn't happen too often. So, yeah, did that answer the question? See how this is getting on. Okay, so it's finished. So that's actually pretty quick. So the Python code, I mean, it's pretty right. It's mapped it back to the lines in the Python. This del method, yeah, it's got this. So the first bad state. So it gives me these timestamps. So this is quite nice. So I can, like, if I want to test it, make sure it's not lying to me. Take that timestamp. And I can see, yeah, okay, so there's some sort of free thing happening there. And yeah, that looks all legit. Okay, deallocation of this object. I don't understand the Python implementation sort of well enough, but I believe this looks right for me from what I understand. So it's got a weak reference to this cached object. Basically, it's a bug with the references. It keeps these objects and the reference counting, and it ends up doing a use after free. Yeah, that took the Python developers a couple of weeks, and this just finds it. So yeah, we can think about how to design these things kind of in the abstract, because I'm showing you the one that we've made at Undo. There are others available as we've discussed already, and they have different sort of pros and cons and trade-offs. But the big design decision is, am I going to store all the states, or I'm going to do it through re-execution? And there are other implementations of this which store all the states. They generally don't work very well. So GDB, for example, has inbuilt time travel debugging, and it's very, very slow and memory hungry. Basically, you want to re-execute because effectively what you get is an enormous compression, if you like. Design decision 2, this gets into, there was a question kind of on this. What's the granularity? What's the level at which we're going to record? And so you could record like individual threads or functions. You could record process level. You could record it like at the JVM if this is a Java thing, or you know, or JavaScript or .NET kind of thing. You could record. So for example, we at Undo we support Java. And the way we do it is we record the entire Java process, the JVM and everything, because it's just a process, right? You just have the JVM at the bottom of that process, and then it's got the Java code. We just record that process. Well, you could decide, I'm not going to do that. I'm not going to record the JVM because I kind of trust that. I'm going to record just the Java program running inside the JVM, on top of the JVM. Or you can do it at the VM level, so kind of VMware style virtual machine. So most of these implementations actually do it at the process level. Process level turns out to be the right answer. You get everything inside the process. So I've got libc and libm and any other libraries. They're all recorded. And the reason is the operating system gives you a very well-defined kind of OS ABI boundary, right? It really defines what a process is, what's in it, what's outside of it. Even something like the JVM, it gets really fuzzy, and you get JNI type, Java native interface calls, and it turns out to be really quite fuzzy and not just not practical. But it works very well at the process level. The other one that works is the VM level. So there are some virtual machine-based implementations of time travel, and that also works. But even interestingly, there's one for web applications called replay.io, and even that, and so it's to JavaScript web application viewer, they record the browser. They have their own special browser, and they've got two actually. They've got a fork of Firefox and they've got a fork of Chrome, and they record the entire browser with the web application running inside it, because it's just the process boundary is the place to do it. The Microsoft .NET IntelliTrace stuff uses the IDNA stuff that was invented for the C++ time travel debugging, like underneath this. It's like basically everybody does it at the process level. And we've got to track time as well. And that's harder than you might think, because you have to track it very precisely. If you imagine, especially if I'm doing this re-execution thing, because let's imagine I've been round a loop like 99 iterations. I'm stepping back through lines in that loop, and when I'm replaying from that snapshot, I've got to replay precisely the right number of iterations of that loop. Otherwise, I'm going to be all over the shop, right? And if I'm replaying asynchronous events like a SIG alarm or something, that has to be replayed. Like, the trouble with this re-execution approach is it's really like finicky. You have to get it bang on, otherwise it goes horribly wrong. In fact, as an irony, these systems are some of the hardest to debug when they do go wrong. At least they were until we got to the point where we could eat our own dog food, and then that was kind of a sort of singularity kind of moment. Everything got a lot easier when we could eat our own dog food, but it took quite a long time to get there. But yeah, you've got to track time very precisely. We need to know, like, we need to be able to identify it's this instruction in that program run through, not the one after, not the same instruction, the next iteration of a loop after, like this precise instruction. And so you can, it's hard to do. You can on some modern CPUs, they have sufficiently accurate performance counters that it does basically work, and that's what RR stands for record and replay. It's a Linux open source kind of equivalent of what we have, and they use the performance counters. And there's a bunch of caveats, and like it certainly doesn't work in like multi-tenant cloud, because like if side channel attacks, they don't want those performance counters to be exported to those they turn off the performance counters. Certain CPUs just doesn't work, etc., etc. But where it does work, it works well. So you can use the performance counters. The other way to do it is to JIT, and that's what we do. We do a just-in-time, about the colors there, I'm not quite sure what's going on. But anyway, we do a just-in-time translation of the machine code as it's running. So we get a copy of the code that's functionally equivalent, but has enough kind of hooks in that we can get our fingers in and tease out what we need, including, and we basically count the number of branches. In fact, we count the number of backwards taken branches. And so the number of backwards taken branches concatenated with the program counter gives you a unique point in program execution history, and that's how we keep track of that. The advantage of doing it, that kind of JIT runtime thing, I mean, the disadvantage is it's a lot of work, and in the simplest kind of straight line performance benchmarks, there's a little bit of overhead, not as much as you might think, but there is some. But the advantage is it works anywhere. You don't have any requirement, and any special, it's not works on this CPU, not that CPU, works in the cloud, not on the cloud, just works everywhere. So it's entirely software. And it also lets you do other things, such as instrumenting shared memory reads. So the way that we do shared memory is quite fun. So then it took us quite a long time to figure out how to do this, but you've got, remember I said that, so shared memory is memory that might change under my feet. And so every time I access that piece of shared memory, I need to check, has it changed? And that's, a little bit of overhead. The vast majority of programs, the vast majority of memory is not shared. Most of the accesses will be to the stack. That's not shared, or just a regular, heap. So we kind of don't want to be checking every single memory access to see whether it's shared, because that's slow for everything. So the other option is you could use the MMU. So you could say, well, we set up the shared memory so that we take a fault when you access the shared memory, which is good because it means that the not shared memory will run, that goes at full speed, completely unencumbered and uninstrumented. But it's bad because taking a fault is like really slow. Taking a fault, fixing up that fault, seeing that you're talking like millions and millions of CPU cycles when you do that. So one way makes every memory access go a little bit slow, and the other way makes the shared memory accesses go really slow. So what we do is kind of a combination, and we set it up so that we'll get a memory fault the first time we access some shared memory. We now know that that instruction, at least sometimes, accesses shared memory. So now we can retranslate that particular instruction differently to check whether it's going to access shared memory, and the ones that don't hit shared memory, they never fault, they don't get retranslated in that way, and they run at full speed. So there's a bunch of things you can do there. Non-deterministic instructions are another kind of example of dealing with that. So yeah. Now, having said that, so the Microsoft one is interesting, TTD. That uses a slightly different approach because, well, so the issue is that Linux, there's about, depending on exactly how you count, there's something in the region of 500 distinct system calls on Linux, which is a bit of a pain to work out what every single one does and trap them and record them away, but it's doable. Windows has thousands of system calls. Nobody knows what they all do, not even Microsoft. So that's why Microsoft had to do it, kind of a different approach, which is they essentially treat all the memory as shared and check every single shared memory access. Did it change or not? Also, even the Windows kernel ABI is not even stable. Like the stable ABI is at the Win32 boundary, not at the kernel level. They're kind of allowed to change that. Whereas Linux keeps its ABI remarkably stable, actually. I have to say, I mean, we care more than anybody else would, way more than anybody else would care about the kernel ABI remaining stable. Like the smallest change, one bit changing in one field structure moving around or something, and that would trip us up. And it has happened only, we've been at this now for the very beginnings of this go back 20 years, and it's happened like 2 or 3 times that they've broken the ABI compatibility. One of them, in fact, we reported it on the kernel mailing list, and Linus himself responded within a couple of hours and had a patch out to fix it. They take it very seriously. So yeah, not all approaches are available to all platforms. The nice thing of doing it the way that TTT on Windows does it is they actually can genuinely record multiple threads in parallel. So if you have a very parallel program, that can have that can actually be a win in terms of performance. But for a smaller number of threads, it will be a lot slower. So it's sort of pros and cons. So yeah, that's what I was talking about with thread serialization. When I talk about thread serialization, a lot of people immediately think, well, that means that we can't capture race conditions. Well, the race condition is going to go away, so I'm serializing all the threads. That's not true. The thread scheduling is preemptive. We allow allow the kernel to choose what threads to run, except we force it to only run one at a time, but it can interrupt at any point. And in fact, we have something we call thread fuzzing, which does deliberately provocative scheduling to make race conditions more likely to reoccur rather than less. And then once you've got a race condition in the recording, it then becomes almost trivial to debug. So here are a few different sort of design decisions and the different implementations of this. There are more. This is not an exhaustive list by any means, but it gives a nice kind of representation. So undo gets everything. You'll notice nearly everything is at the boundary layer of the process, except for this thing ODB. ODB stands for the Omniscient Debugger. It's a Java implementation, which is the very first thing I saw that did this and blew my mind. And I was like, as a C programmer, I wish I had that available to me. And then for the next, whatever it was, year or two, it was like bouncing around in my mind until we figured out how to make it work. But that worked at the JVM level on the process level. Binary rewriting, so you can see, Windows TTD does that, we do that, other things don't. Those are kind of the different trade-offs. I won't go through every single box in that table because it'll be a bit boring. That's it. Bang on time. How about that? Any other questions?
Platforms. So what platforms can I run this on?
Any Linux, basically, and x86 or ARM.
Can I run it on a Mac?
Well, we can inside a Docker container. Yeah, Mac is the only platform it's only mainstream platform not to have this. It's I don't know why. Just there's sort of just business reasons why we haven't invested in doing that. It's a smaller niche market. I thought Apple might care enough to do it, but so far not.
What sort of issues did you run into trying to teach Claude how to use your debugger?
That's a fun question. So we've got two different MCP servers, two approaches that I showed you. So the first one is basically just trying to get Claude to just use the tool, right? And this became possible kind of earlier this year when MCP became a thing, and MCP is allowing LLMs to use tools. LLMs do not like traditional debugger sort of concepts. It would get immediately confused about it, like it would set a breakpoint, forget that it set a breakpoint, hit the breakpoint, and then say, oh, something's gone wrong. Or it would do the opposite. It would sort of expect a breakpoint to be there because it's just thought about it. And it would say, I'm going to run until this function. Oh, didn't see that function, therefore that didn't get called. It's like, no, you didn't set a breakpoint. So they don't like that kind of stateful kind of, that kind of way of working. It didn't work super well. So, but we've got one MCP server that does drive undo. That's the explain thing that I was showing. So what we did there was to basically take away almost everything. And we took away forward execution because it just kept getting confused and going back and forth. We've given it just like it's only got it can go back to when the data changed. So it's got that go back to when this last changed. It's got go back into the last time this function was called or returned, and one or two other things. And that kind of we found that works better, much better. But it still has some kind of scalability issues. So the one that works is one that we're more excited about is this way of teasing out the logs. And we just say, here's a program execution. What logs do you wish were there? And then it just keeps asking about the logs, and that seems to work. That seems to work the best. Yeah. They're not, I think it's been an interesting journey, because the LLMs really do feel magical. I mean, it's amazing what they can do and what they can generate and things. it's easy to fall into. I had this described really well that for like, since ancient philosophers, people have asked the question of, can you have thought without language? And who knows? But now we have to ask, can you have language without thought? And I think with the LLMs, you kind of can. And so, yeah, the stuff that you would think would be quite easy for them to do in terms of tool use, they really, really struggle with. So yeah, you want large amounts of data in and out, and get the large amount of data in, have it chew on that, fill up the context window with relevant context, and then it gives the good answers.
I have to say that's interesting, because I was debugging a CMake at one point and asked the Chat GPT or one of them, help me with this, and said, give me these logs. I gave it those logs. It gave me the answer. It's kind of out of the other opposite way from what you did.
Well, it's kind of
the same thing.
It's the same thing, but
it asked for them in my case.
Yeah, exactly. Allow it to do that. Allow it to ask the logs it wants, and that seems to work better. But actually, driving an interactive debugger, they're just not good at that.
Yeah, and the interesting thing was, once it found it in the log, it was obvious. But the log was so huge, I never would have found it.
Yeah, right.
It's got the capability to analyze and ingest a ridiculous amount of information, where human doesn't.
Right. Human can ingest like 7 or 9 bits of information or something, and these things now have context windows, and in many hundreds of thousands, maybe even millions.
That's interesting in itself.
But then it does, the thing with the logs is, and in general, I think with contexts for LLMs is, you want to give it as much of the relevant context as you can, and as little as the irrelevant context. So, most of the benchmarks and how good are they debugging things, they're like 50 lines of Python with a bug in it, right? That's a very high bug density. So you've got to find one line out of the 50. Whereas in the real world, you're more likely looking at, probably millions of lines of code with there's probably lots of bad lines in there, but you're looking for one particular one. So even though the context windows are getting very large, it still works much better if you feed it in, if you don't distract it with irrelevant context.
I have a question on your MCP server.
Yeah.
So when you ask the tool to explain where the bug is in your command, and feed it the snapshot file, what was actually going on in the background? Is it as if it's simulating each and every execution of the program, and then trying to understand from each of those, and then trying to rationalize what could be wrong? Or how is that done? Is the usual prompt, but
so let's look a bit more deep. So I think I've just realized what went wrong in the so this one that, okay, hang on. I think I've got the history of it up here. It's going to take forever. Right, so right, so this was it. So you can see what it tells you what it's doing. So I said, explain, find the time. But yeah, I've just remembered what's going on. So there's in the latest version of Claude Code, for some reason, Claude Code, when it's spun up tools, if they're still there after a while, it just kills them. It literally just sends them a sig term to kill them, to clean up, and it's pretty indiscriminate about what it sig terms. So I think and we had fixed up one of them. I say fixed, we'd actually just told that this particular program that kept getting killed by Claude to ignore sig term. I'm not proud of it, but it was enough. I think looking at this, Claude Code's now sending sig term to a different part of the system, and that hopefully we can persuade Anthropic to address that, because that's problematic. Anyway, so so I said explain the time program execution where the second zombie was killed. So it says, right, yeah, I'll try and do that. And it's going to make a debugger call, and it's info bookmark. So it's going to say, are there any bookmarks set in this debug history? Because that's probably a good place to start. That might give some context. There aren't. So then it does this other debugger called end. So it's going to go to the very end of time, because as I said, we've actually we've given it, we just find this works better. It can only go to the end of time and then work back, rather than go to the beginning and walk forward, or go to the middle and walk forward, because it gets in these endless loops of going back and forth. So so it goes to the end. Get a backtrace. So that's one of the things it's got. So you can see is anything interesting in there. Then then Claude decides Claude Code decides it's going to start doing some grep. Claude Code likes doing that. All good. Read some source code, and then it starts kind of find out about it. Starts to build up a picture of like what zombies are, and these empty possessed and empty shot guy and stuff. And then oh no, it's the recursive internal problem. That's another. Yeah, that is a Claude Code bug. I've seen that before. Claude Code does get it, but you can see, and then it's doing this last value. So then it says, okay, I've found something. Let me do an expression on that kill mob, and you know what? I wonder whether. So that was, I think, because I did it twice and it failed in the same way. So there's something about that recording that is just confusing it. But I tested this earlier. Okay, hang on. Why can't I see? Okay, that's annoying. It worked. So let me take a previous recording. I think I have more luck with that one, which I was just testing it this morning. Extend, explain. And yeah, it will. We'll see some of the things it starts doing. But you can see it's a pretty. I think I have more luck here. It's a pretty small set of commands that we've exposed to it, and they were better.
So in terms of cost with, so you're paying Anthropic, I'm guessing.
Yeah.
What's a typical like example cost for like a debugging session here? Are we talking dollars, tens of dollars, pennies? Pennies
for something like this. I mean, for a big one might get into like $1 or $2 if it's a significant. I mean,
pretty trivial cost.
I mean, compared to the cost of hiring a programmer.
Yeah, exactly. Yeah. Totally trivial cost.
Yeah.
So does the Linux IOUing present a particular problem?
Yes.
Sounds like it's
Yes. So that's one where, so we don't currently support OU-ring. Nothing does. We know how to do it, and we've got a couple of customers. I think we're going to have to do it at some point in the next kind of 6 months, because we know how to, because we can deal with shared memory. So it's basically a special case of shared memory. We just need to add the. We can already deal with the old school async IO, so that all just works. So we just need to extend that for IOU-ring. I mean, I can say just because it's not me who has to do the work. Yeah.
In general, when like LLMs hallucinate, for example, like the problem is that the main reasoning engine behind the LLM will, get convinced of the wrong idea and kind of push that idea onto something that doesn't work, right? So my understanding is what this tool does is it, gives the MCP server to provide a much smoother interface to the debugger, right? So that this tool can catch on to I guess its wrong approach is a lot quicker.
Right.
Like Claude can catch on to bad decisions.
Yes.
Right. My question is it like, have you still had situations where like Claude has some bad reasoning and then uses the tool in an ineffective way because of that?
Yeah.
Right?
Yeah. So particularly with this version of it, where it's using the tool, yes, like it can get itself in a bit of a
In a-
spiral, and yes, with the other version that I showed you, which is the more logging based approach.
Right.
In fact, I haven't got that to show you now, but what we're working on internally, which does look really promising, is kind of adversarial approach. So we have two agents. One comes up with a hypothesis for what the bug is, and then there's another one that kind of grades its homework. And it's so it's
like a generative discriminative.
exactly.
Okay.
And that seems to work really well. It's also quite fun watching because they get a bit sycophantic.
Yep.
So they start encouraging each other in this really kind of cute way. It's well, it's a great idea, but I think you're not quite there. Maybe keep going. I'm sure you can get there. And it goes,
So let's come up with an answer. Can we
Yeah.
check the answer by
Yeah.
looking at the frame?
yeah, absolutely. So yeah, so it's bookmarked the second zombie kill. So yeah, let's look at the frame. I've got to open that window. Okay, so if I now put that breakpoint on display, continue that and finish. There you go. That's definitely it.
This one has to have blood splatter.
Yeah. It's amazing how gross it can be in such low res, isn't it? But yeah. So you can see it actually usually takes a different approach than I took, which is fine. So what it does usually, so it's always a bit different. But yeah, so it's latched onto. It's found. I didn't find this when I did it. It's found a thing called players kill count. So it said, I can use that and look on the player, and it kind of tracks that value to work out when it was, which is fine. Do it a different way.
So it really is exploring and ingesting and
Yep. This is also quite fun. If I do so if I put a breakpoint, I'll put a breakpoint on display. What you can do in GDB, you can hang commands off of a breakpoint. So if I just do a continue every time we hit that display breakpoint, it should, you can see it's as a replay of the run through of the game. So it's, obviously replays a bit faster than the original. But you can actually, I can set it up right, but you can actually see when it's running, we didn't leave the window open, but you can actually see the different parts of the game through where Claude is now looking, because it updates the video buffer, which is quite nice.
we got about 10 minutes left, folks.
Oh yeah.
Yeah, I'm probably the only person in the room who hadn't really ever heard of time travel debuggers before coming here, so you'll have to excuse it if any of this question is trivial. In general, I've found that performance bugs, when you can think about, pulse sharing and network and things like that, right, where are a lot harder to debug, and the LLMs, like I've handed those to LLMs, and those have been kind of flaky when it comes to debugging.
Yeah.
What would be, I guess, in general, from a human perspective, how would I go about, what would be my process for inspecting that performance type bugs? Where it runs correctly, it just uses way more CPU costs than this.
Yeah.
And then how would that came when I give it to an LLM?
Right. So I think for so the question was about performance bugs and how would you apply this to performance bugs. There's actually, I think, performance bugs very broadly go into two buckets. One is algorithmic, or maybe I've got some kind of order n squared thing or something, and the other one is more kind of micro, cache line, bouncing and fault sharing and all that kind of stuff, right? It doesn't really work for that one, but that's like in fact, this technology won't really work for that one because it changes we try very hard to change the program as little as possible when we're running it, but cache lines and things, there's just too much variation going on with our code's running at the same time.
Yeah.
But for the algorithmic stuff, then that's a different story. That works really well.
No, yeah.
And so yeah, you got like, because you end up with like something's order n squared. But no one expects it to be order n squared, right? We never write that on purpose, but it's easy to do by mistake, and then you can kind of figure out. And often it's not trivial how it has ended up happening. And then it's good. I mean, in fact, we had a customer, I think a couple of weeks ago, and we showed this to them so that we sort of cut. No, it's a bit longer. Anyway, we rolled this out to people for only 3 or 4 weeks ago, and yeah, we were on a call with the customer, and they said, "Oh, this is really good. Can we use it to explore this performance issue we've got?" And we said, "Try. I don't know," and it worked. So yeah, for algorithm stuff, it can be cool. One thing we found actually it's fascinating with doing kind of user studies. So we built this thing. It's you ask these very high level questions, and it's super cool. We gave this to a couple of users in our customers, and this has happened several times now. First thing they type is, "Please set a breakpoint on line 42." And we're like, no, you don't do that. Like, ask the question right at the top. Just ask like, what the hell is going on? Because people kind of, it's just how they're used to like thinking and working. And actually, if you ask it to do that, it's really bad at it. It's better just to have the old school commands. Yeah.
In my experience, I've seen LLMs don't like not English, and you probably have a lot of binary that you're sending its way. How did you?
No, we're sending it all. It's all English.
It's all English.
Yeah,
no
yeah. We're not sending any binaries.
Anything?
There's a lot of binary, obviously, under the hood, but we don't expose that. Apart from the value of things like when it was looking at the kill count, so there are kind of integer values that get data types. So data, yeah, but it's no, everything that the LLM is seeing is a kind of textual kind of representation of the program where it is and where it is in time. Yeah.
I see. So it never sees it. It looked like it was able to, but maybe it's not.
Well, it is. So, maybe I misunderstood your question. Actually, it is. Oh, gosh, this is going to. It does. There's going to be one of these for every single frame now. Down there. So it will, because it gets pointer values and things like that. Yes, but that's it. They're okay with that because they kind of know what pointers are, and that the actual specifics of what the pointer is not that interesting. Yeah, no, that seems to be. Yeah, they seem happy enough with that. Yeah.
Can you do anything if you just have a core dump, like a loan from a customer?
So in general, LLMs can have. They're quite. I've seen them. They're quite good at just get with a backtrace. Just actually, literally just copy paste a backtrace into ChatGPT or whatever, and it can often deduce things. Generally, I mean, it in terms of like the time travel stuff, there's nothing to be done with the core file because the information is just like not there. I don't know of anybody who's done some. I don't know if anyone's done some work to allow the LLM to kind of poke around in the core file. I think that would be an interesting topic to explore. I don't know that anybody's actually tried that. Yeah, giving it an MCP server to poke around in a core file and see what it can figure out, that could be quite interesting. Yeah, that's a good idea.
And then the other question I have, what if the problem doesn't reproduce when it's running on the board?
Yeah, then that sucks.
Good answer.
I mean, we try to make that. I mean, that does suck. So we try very hard to make that not be the case. We do things like thread fuzzing that I described. We generally try and be as high fidelity and as out of the way as we possibly can be. In my very approximate and I guess somewhat biased estimation, the vast majority of issues will reproduce under recording. Like what percentage I give it, but like 70–80% will reproduce. But you will sometimes get things that just can't reproduce under recording, and then yeah.
I get my money back.
No. Well, I guess you could choose not to renew. Everyone renews.
We probably have time for one more, folks. Going once, going twice. Yeah, we hit the time about right.
There you go. Awesome.
We're out of lecture and out of questions.
Cool. Well, thank you very much, everybody. That was good discussion. Good question.
It was a fascinating presentation. Thank you very much for coming here and presenting to us tonight.
Oh yeah,
Yes,
no,
thank
thank
you.
you. Thank you for having me.
If you get the slides to me too, send me the slides
Yep.
and I'll
No problem.
get
Yep.
it posted with the video.
Yep, we'll do that.
Okay.
Okay, thanks, folks. I'm going to stop the recording here.
Thanks, Lloyd.